uses coupled surface water and groundwater modeling for water supply assessment, the case of Mananga Watershed, Cebu, Philippines. This paper will be presented by Melvin Raymond G. Dangil, who has a Master of Science in Civil Engineering degree, particularly in water resources, and works for the USC Water Resources Center, or WRC Foundation Incorporated. Let us now welcome Engineer Dangil for his presentation.
Good afternoon, everyone. So, this is the title of my study. Actually, this is my master's thesis, presented for a good 60 minutes, but for this presentation, it's going to be just 20 minutes, so hope it works. So I'd like to begin by sharing a bit about Metro Cebu's water supply, demand, and supply as well. So, just in case not everyone is knowledgeable where your water from your faucets come from, 70% of that, if you're connected with MCWD, it's roughly 70% of that comes from groundwater. It's water from beneath. And the remaining is from surface water, as well as brackish water. So in recent years, the brackish part has been steadily increasing because of new players on the desalination field. So, but essentially, right now, we're still heavily reliant on groundwater. As you can see in the image on the right, those points are actually locations of our groundwater wells. And the blue ones are by MCWD, and the ones that are colored yellow are private wells. And for this image on the left, that is one of our surface water sources in Talisay called the Akupan Weir. This one is the sedimentation basin. Okay, so as for demand, it has steadily been increasing. This one is from a study from JICA of 2010, but still the data is very much relevant that we have been increasing in terms of population size. As of 2020, that's reached 3 million, and as of 2023, water demand is estimated to be 500,000 cubic meters per day. So with that, there's a deficit, clear deficit in terms of water supply of about 200,000 cubic meters per day. So of course, we have been doing a lot of studies to improve and help on that. Apart from all the desalination developments recently, historically, we have been eyeing this Mananga Watershed as a water source. So Mananga Watershed has an area of 8,600 hectares, and since the 1980s, we've been studying this location, and up until 91, 2000, in terms of its feasibility, and studies show that it is very much feasible, but we have not really been implemented it. So it's been reviewed repeatedly. Even groundwater models have been also developed for the whole Cebu, for that matter. And then there's this concept about this surface water and groundwater connection. So these two sources are very much interrelated. They're connected, and primarily connected through rivers, because some rivers, when the water level is lower compared to that of the groundwater, the river will receive water from the groundwater resource, so that becomes a gaining stream. It gains water from the groundwater resource. Now, if in case the rivers have higher water level and the neighboring groundwater is lower, then the water then loses its water towards the groundwater aquifers nearby. So this phenomenon has been studied internationally for many years, and even approach on modeling has been done. So despite the efforts of trying to diversify our resources so that we won't be very much reliant on groundwater, there are limited studies on this interconnectedness for surface water and groundwater. So especially for Mananga. And this study aims to understand that connection between those two resources, hoping that we could harness both resources conjunctively, together. And if there's a better way to use those, depending on the time of the year. So the model can offer insights in terms of how we use our resource and what its impact on to the other resource when you start to develop surface water, and how does that affect to the groundwater and vice versa. So all of this efforts is towards our goal to have an integrated watershed management, integrated water resource management. All right, so this is how it works. Since my title says coupled surface water and groundwater modeling, it involves two types of model. The surface water, which is the hydrologic model, it computes for our surface flows, and then the groundwater model, which is the computes for our water levels, our pumping rates, all of that. Right. So from your left, you see the inputs. So SWAT is the model that we use for the hydrologic computations. So that's the soil and water assessment tool. And for the groundwater, that's the modular three-dimensional flow model, or MODFLOW in short. So both models have varying inputs that I will show quickly in the coming slides. As for its outputs, what we really want to know is how much water is discharged through this huge watershed, and maybe how much could be harnessed for that matter. And the water levels, the groundwater levels, to be more specific, we want to see how it moves throughout the varying periods of droughts and rainy seasons. And with that, how these two sources are interacting with each other, with the surface water and the groundwater, and more importantly, the water balance, right? So we really want to have a good accounting of where the water goes, from the rainfall, how does it go towards the discharges, the recharge, percolation, and what have you. So that's how it works. Whatever it is, so the SWAT model computes discharge, even the recharge as well, and it transfers that data as groundwater recharge to our surface and even to the rivers, and it discharges that, and it's interacting model. It's a coupled model. So the same way we cook our food, that's how you do modeling. You start off by collecting data, a lot of it, and then you slice them up and make them fit what your model requires, and run the model, and then you calibrate it just so that it would actually capture or at least mimic the closest thing to reality, and as long as it is in acceptable values. And then eventually, once you have that first baseline set up, you can now do some management scenarios, which really gives the best value of your model. You start to explore what if, So we'll see more of that in later slides. So these are some of the inputs, the setup. So topography, we use that as an input. Land cover, this is from a 2015 land cover Namibia dataset. Soil, it's from FAO, it's a global dataset. Weather data are from Bonbon and Mactan Station. Also, I incorporated a global dataset called CSFR just for those times that there are data gaps. And meteorological data comprises precipitation, temperature, wind speed, relative humidity, and solar radiation. So there's a warm-up period when you do the modeling, so as somehow it gives the model some time to settle, and until you can able to calibrate it with available observed data sets. And then lastly, you validate your results. If it still gives out satisfactory, say, statistics, then you do it for other years in this case. So I can discuss this. Agricultural, forest, bushland. Yep. Yeah, it's worth noting that Mananga Watershed actually has majority very steep slopes. You know, it's 60% of the watershed has a slope of above 50%, right? So it's very steep. So you can actually start to imagine how that impacts your water balance in terms of runoff, evaporation, what have you. So rainfall data. This actually is go for any modeling study, for any hydrologic or even groundwater study. We are very much lucky that the MCWD and with the help of the Water Resource Center been doing this for many, many years. So this allows us to do these models like this. So especially for Bonbon. Bonbon is a mountain station. It has about 1,800 rainfall average, annual rainfall average, compared to that of Mactan, which has only around 1.6. So you clearly see the variability in terms of distribution of the rainfall above the area. So you can't just simply use right away Mactan just so because it's available. So it's very important to have this really local station to capture local meteorological phenomena. Alright, so also temperature, we're able to, although I think this one's from Mactan. And river discharges, this also from MCWD and WRC, been doing this for many years. So what we have is a 2010 to 2020 data set. So it allows us to actually use this to compare this to our output. River discharges is how we calibrate our model. We know how true it is, you know how much we could rely on it in terms of our management scenarios. So if you can see the yellow dot on the inset map, that's the location of the rain gauge, and the red one is the location of the river discharge monitoring, or this one. And you see how far Mactan is. But still, we incorporated to have this more robust meteorological model input. Okay, so for the groundwater, the concept for groundwater modeling is you technically just discretize the surface that you have, and you determine how many, it depends on the input, but in my case, I used 100 by 100 meter discretization with 3 layers. The 3 layers have been determined because of available geological data, which you will see in a while. Essentially, it follows the same modeling concept where you do warm-up, and then you do calibration, and then you also do validation. So these are the boundary conditions on the right table for the bottom. Alright, so these are the geologic data from which it's based off. So essentially, majority of the top layers you have some Karkar limestone and alluvial downstream, but essentially when you get upstream, geologic formations becomes older and less porous. But there are still some that are quite porous, like the Mananga formation as well. But you get to deeper depths, then you reach the bedrock or some sort of the basement of your geologic formation for the whole watershed. Right, so variable locations is very much important because we're taking out water from the watershed, from the aquifer. Then well ecologies, these we know how, although maps offer useful information, they are macro informations. We need also like somehow in situ information of the groundwater. Of the geologic conditions. Well abstraction rates as well. This one, our desired output is the piezometric levels. So we try to calibrate our model based on these observations. Unfortunately, I was only able to use one well because apparently the other observations are a bit erratic, and my advisor and I decided to let them go, at least for this case. So now for the results of our baseline study, we are able to calibrate it to a 0.5 national efficiency statistical model, statistical parameter. So this NSE actually is more common in hydrologic studies. We commonly use that to assess the effectiveness of the model. So 0.5 actually, although it looks low, but it actually is satisfactory in this case. So we went with that and validated our results to have a similar NEC. So the water balance appears to have, for a rainfall, annual average rainfall, almost half of that goes and evaporates to our atmosphere, and a little bit more of a third is runoff. It goes to our rivers, and some, which is 6%, groundwater flows. So, and lastly, the percolation, which actually on recharge to the groundwater is 9%. So these are the sensitive parameters in the table, the seeding table. And lastly, this part of the calibration is for our groundwater. So our general water budget for the full duration will show somehow a negative change in our storage. That means we have been abstracting more than what is coming in to our aquifers. So that's one key information that we've learned from this study. And also, the next table is the geologic parameters that we use to represent hydraulic conductivity, specific yield, specific storage for the model. So you really want to look at things visually, so and seasonally. So during wet season, it's here that the water table suggests that there's the water movement is towards the river, which is a given. So this means that the rivers are gaining. They're considered as gaining streams. When we get to a dry season, now you could more see vividly the cone of depression. So this cone of depression occurs when there's abstraction in groundwater. So on the right side, just yeah. And finally, the surface water and the groundwater interaction. So this is a fairly new result compared to other studies because we are able to see the spatial variety of the groundwater discharge and recharge along the river network. So as you can see, somewhere in the midstream it's gaining, somewhere a little bit after, now it becomes losing stream, and then it becomes gaining again, and then losing. So there's a lot of variability. But it's also important to note that one of the key factors that is very, very difficult to calibrate is your river parameters. River parameters are very tricky, so you have to also consider what studies support your calibration values. So, yeah. And then we get to scenario analysis. So for my study, I did 5. So actually, I have 4. The fourth is a mix of 1 and 3, but I decided not to present it here because it's just very similar to the other first and third. All right, so scenario 1 is we want to meet the supply by increasing our abstraction downstream. So we try to say Q times 2 in a way, if that's permissible. So what happens is, as expected, groundwater level for the downstream is very much affected. The cone of depression has been increased with a change in up to 7 meters of difference. Now this 3 figures show the groundwater level on baseline pumping. Then when you double it, what happens, and then you subtract those values, you get this change, groundwater levels. And then what if now we wanted to increase the height of the Paklupan weir, as suggested by the former study Kawok from AG. And then it shows that, this is still the scenario. Scenario 2 is increasing the pumping rates from the Paklupan area. So essentially, no changes have been observed in the downstream aquifer by increasing upstream pumping. And the third scenario is when we try to increase the heads of the Paklupan weir by 2 meters. So in this case, there is an effect on the groundwater levels by as much as 1 meter or so. Now for scenario 5, we attempted to model what if we build the Mananga Dam, and so with that, this changes in terms of your discharge downstream, right? Because you're trying to store water in your reservoir. So now what happens is you see on the flow hydrograph on the right side, the blue lines actually show the observed, and when you try to simulate that there's a dam in there, you only set environmental flows to flow, or depends on what you want, and then now it just discharges when your storage is surpassed, which happens in sometime 2017. There's a very big increase in discharge. So what happens when you do that is, since the surface water and groundwater are very much connected, the groundwater level also has been impacted based on baseline compared to the scenario 5. There's been a decrease of around 1 meter in that area, that location. So 1 meter to 2 meters. So that's something to consider when you're trying to develop the water resource as a whole. All right, so now we're down to our conclusions. So with the model, the SWAT-MODFLOW model that we've developed, we were able to find out that runoff is 37% for Mananga Watershed, evapotranspiration is 49%, groundwater flow is 9%, and the percolation is 9%. So wells account for 35% of the water coming out from our groundwater aquifers, as estimated from the available data sets. It was also found that both resources are linked and are spatially and seasonally variable. Groundwater extractions have an impact on our surface water as expected, and also the rising head of aquifers may affect our piezometric levels in the Mananga well field downstream. So the Mananga Dam, should it be built, would have effect also on our groundwater as well. Not because they are interconnected, these two are of different geologic formations, but in terms of the amount of water recharging through rivers. And lastly, geology is a crucial parameter or factor in defining our integrated surface water and groundwater model. So, thank you very much.
Thank you. Thank you, Engineer Daniel, for your paper.